Okay, so I usually like to start off these videos by saying that I'm not going to make this long, but this is one of those topics that I really want to make sure I explain as well as possible. Just because this is just something that always comes up on the AP exam. It's also something that you would always, well, something that colleges in general just emphasize a lot. So we're going to talk about straight line motion. For those of you who have taken physics before or are good at physics, some of this might seem very familiar to you. And, you might be able to solve some of your physics problems using calculus instead. So let's kind of look at the first question. It says a tennis ball is being thrown straight up into the air. The height of the ball is modeled by S of t. This is the position. So the S of t is equal to negative 4.9t squared plus 18t plus 2. So you'll notice this, of course, is a parabola with the leading coefficient being negative. So it's going to be a parabola facing down. And you can just kind of look to see that, there's the ball. And that's the position of the ball if you were to just kind of like, throw it up in the air. Now you'll notice that the initial height here is, we'll just go ahead and assume that that's like the height maybe in meters of the person throwing the ball. Because that's where that'll be the starting position. But more important than that is understanding what is the velocity and acceleration in relation to this position function. Okay, so, well, one of the things that I'm going to cover a little bit more in detail right here is that you should know that the velocity is essentially the position or the derivative of the position function. Okay. So the velocity function is the derivative of this position function. And the acceleration, okay, is the derivative of the velocity function, or really the second derivative of the position. Okay, so really as you kind of go from position to velocity to acceleration, you're essentially just taking the derivative to get to the next part. Okay, now let's kind of think about what the graphs will look like. And throughout this course, you're going to start seeing me actually go back and forth between, original function, derivative, second derivative function, because I think it's important for us to kind of just look back and forth and not get confused with all of that. So first of all, if you know that the velocity is the derivative of the position function, well, just kind of pay attention here. You'll notice that like the slopes, right? I mean, they're kind of going upward, uphill, uphill, uphill. The slopes of the velocity function is positive, right? So we know that, and really where it becomes 0 is right there, because that's a slope of 0. So we kind of know that at this x value, let me just kind of like draw right there. So like just a little bit below 2, we know that at that x value, the velocity is 0. Now, anything below 2, we know that the slopes are positive. And if the slopes are positive, then that means that our velocity is positive. But what you'll notice here is that right after the 0, you'll notice that now all of the slopes are kind of going downhill, right? In other words, the velocity is going to be negative at that point, which kind of makes sense. Like, if velocity is, if you're thinking about the direction of velocity, if you were to throw a ball upward, right, it's going to, go in a positive direction and kind of, go up, but then it's going to start slowing down, get to 0, stay at rest, and then go in the opposite direction. So what the velocity function is going to look like here, let me just kind of get my ruler, it's going to probably look something like this. Right? I mean, this maybe off by a small margin, but whatever. It's just, you just have to understand kind of what's going on here. Right, so the velocity is, is positive, right? It's positive when you think like to the left of this value, and to the right of this value, the velocity starts becoming negative, and that's all related to the slopes of that function. Now, if you kind of think about the acceleration graph, well, if I went ahead and I took the second derivative of this whole thing, like, obviously the first derivative will be like negative 9.8t plus 18, and then the second derivative will just be negative 9.8, right? And it's just going to be a constant. So for those of you who, are taking AP physics, you probably understand that, or should know, that the velocity is, the acceleration, and we should know that that's the acceleration due to gravity, is negative 9.81. All right, so that's just kind of a brief overview of, kind of going back and forth between graphs of initial function, derivative, second derivative, in this case, and specifically for position, velocity, and acceleration. All right, now as far as average velocity is concerned, that's pretty much just, you're going to be thinking about the rate of change for the position function. So you're just going to think of S of B minus S of A over B minus A. If you know that the velocity is the derivative of position, and you want to find like the instance, like, the average rate of change for that, you can pretty much use an estimate with that slope. And then the other thing you have to understand is that the speed is the absolute value of velocity. All right. It's just kind of like with a car. Like if you're driving down, maybe you're driving in this direction, right? And we consider this to be positive, right? Maybe we would consider that as like positive 50 miles per hour, right? But if you're driving in this direction, right, then that would be negative 50 miles per hour when you're thinking about velocity. But if we're just thinking about the speed, or if I say, hey, at what speed are you driving, you don't really incorporate the direction. So it's just, your speed is just going to be 50 miles per hour, not necessarily positive or negative. All right. And speaking of which, so really now let's this is going to be helpful for this part. So if we know that the velocity is less than 0, so if we have a negative velocity, then we know that the particle is moving left. So moving left with regards to the x-axis. I put x-axis. Or it could be moving down, right? It depends on where, what exactly you're, like for example, the ball being tossed up, and then as the ball is coming down, it's negative. So on the y-axis, right? If the velocity is greater than 0 or positive, then we know that it's moving to the right, right? On the x-axis, or up on the y-axis. And if it's 0, right, then that means that the particle is rest. If there's no velocity, if it's not speeding up or speeding down, then it is essentially at rest. Particle is at rest. Okay. So, it's kind of a brief overview, but we're going to kind of use a lot of these ideas to go ahead and help us solve all of these problems. So let's talk about whether or not something is speeding up or slowing down. Okay. So, the thing you have to essentially remember, the rule of thumb you have to understand, is that if the velocity and acceleration have the same sign, whether they're both positive or both negative, right? Whether they're both positive or negative, right? Then the particle is speeding up. If the velocity and acceleration have different signs, then the particle is slowing down. Right? And I mean, that kind of makes sense. I wish I had my sticky notes, but I'll just use this paper. That really makes sense, because if you think about it, let's say you're over here and you're running in this direction at, 50 miles per, well, no, you're not going to run 50 miles per hour. I don't know. You're running in this direction and you have a positive velocity, right? If you think about it, if you're accelerating in that direction as well, right? Your velocity is obviously at some value, but you're accelerating, you're increasing your velocity in that same direction, that you're obviously going to be going much, much faster, right? And you're going to be speeding up, right? But if you think about it, let's say, let's say that you're driving a car. Let's draw this. Oh my God, that is one of the worst cars I've ever drawn, but whatever, you get the point. And let's say you're driving a car and you press the brakes. Well, now, the velocity is going in this direction. But if the acceleration is going in the opposite direction, right? Sure, you have momentum with your velocity moving you forward. But if the acceleration is pointing in the other direction, this is almost going to kind of like, counteract the direction of the velocity. And you're actually going to be slowing down, right? I don't know if those visuals helped you, but long story short, if the velocity and acceleration have the same sign, then you're speeding up. Different signs, you're slowing down. All right. So let's just kind of look at this table and kind of make a concluding statement based off like at each of these times. Are we speeding up or are we slowing down? Well, the velocity is going positive this way, but if the acceleration is going negative this way, the acceleration is slowing that down, and they also have different signs. So here we're slowing down. Same thing over here. This time the velocity is going in this direction, but you're accelerating there. So you're actually slowing down again. And again, it has more to do with the different signs. So slowing down. Here, both of them are positive. So, if your velocity and acceleration are going in the same direction, you are actually speeding up. And over here, if your velocity and your acceleration are both going in this direction, then it's speeding up, but in this direction. I missed that mark, whatever. Speeding up. Okay. So, hopefully that makes sense. I mean, really what I'm doing here is I'm just kind of explaining it through vectors. I know physics is a huge fan of, or the subject of physics loves using vectors to explain everything. Now, as far as displacement is concerned, and I know I'm just kind of going over definitions here, but these are all important. Displacement is the net change in position. All right. So as far as displacement is concerned, they don't care how much you've traveled. They just care about where are you relative to where you started. So, let's say you ran around a track, right? And you started over here at this position. That's your starting position, right? If you go around in a big circle, right? Sure, you may have traveled, I don't know how long a track is. Let's just say, let's just say a quarter of a mile, right? I'm probably way off by that, but I don't care. Let's say you go around a park that's a quarter of a mile. How about that? So you go around a park that's a quarter of a mile, and then you start over here, but then you end up at the same place, right? Your displacement is going to be, how do you spell displacement? Displacement is going to be 0, right? Because, your starting position and your ending position are at the same place. So really, at the end of the day, you didn't really end up anywhere. You just went around in a big circle. Your distance, however, right, is essentially just going to be whatever distance you actually traveled. So in this case, it'll be a quarter of a mile. All right, so that's just a bit of a review. And again, if this is physics, then I'm sorry you're bored out of your mind with this. But or if you think about it, like let's say your starting position was here at 0, and you go ahead and you walk all the way over here at 10 meters, and then you walk back maybe 7 meters this way, and then this is where you end up, right? This was your starting position. You go over here, and then you walk over here. Your displacement is actually going to be 10 minus 7 is this right here from where your starting position to where you're currently at right now, and that's 3 meters. All right, so I'm just going to move along. So now here's just a couple of questions about this table. It says, in what direction is the object moving at t equals 1? Well, let's look at t equals 1. So at 1 second, and as far as like in what direction the object is moving, we're going to go ahead and look at the velocity, and we notice that the velocity is -2. So since v of 1 is equal to -2, which is less than 0, I'll just say which is less than 0, the particle is, we're talking about a particle here, yeah. The particle is moving left. Okay. Now, as far as this one, this is going to kind of tie back to some things that we learned in the past. How many times is the velocity at rest? Well, we don't know exactly how many times. It could have been at rest many, many times, but we can go ahead and think about what is the minimum number of times. If you think about it, if the velocity is 3 here, and then the velocity suddenly is -2, that means that at some point it was +3 or moving to the right at some point, but then it switched gears and now it's over here at, you know, somewhere in between -5 and 1, right? Somewhere over here, it had to stop and change direction. So it had to stop and be at rest and then change directions to move the other way, right? So that means we have to at least have 1 0 value in between these two. And hopefully you guys, you know, are already thinking back to our limits chapter and remembering that by, you know, the intermediate value theorem, there must exist a function like that. And of course, in order to prove that, we have to say, okay, well, since the function is differentiable, all coming back to haunt you if you don't remember this, right? So if the function is differentiable, sorry. If the function is differentiable, it's continuous. So the function is differentiable, so it's continuous. My notes were really sloppy again today. I'm so sorry, guys. All right, I feel like it's been forever since I've made a video. So the function is differentiable, so it's continuous. And if the particle is at rest at v of t equals 0, we know by the intermediate value theorem that this will occur at least 3 times, right? And that makes sense because it shifted gears here, so it has to at least happen once. It shifted gears here, so from negative to positive, and obviously it's changing direction again, so it had to be at rest at least one point there. And over here, from -1 to 1, it changes gears again, so there we go. Now, I mean, who's to say that there's, you know, it shifted gears only once? Maybe, you know, maybe they did a whole bunch of zigzags and went back and forth and couldn't make up their mind. It could have happened multiple times in between these seconds. That's unlikely, but it could have happened. But that's why we say at least, where's the phrase, is at rest. We know that this will occur at least 3 times, right? So, you know, we know that the sign of the velocity changes from, you know, -5 to 1, from 1 to 2, and from 2 to 4. So we can for sure say that at least 3 times that it changed position. So let's go ahead and answer these problems on the back. We're at 17 minutes. Nice. All right, so let's go ahead and kind of see particle motion in the form of an equation and in the form of a graph. So I guess really we kind of like, you know, talked about the graphs already, but and now we kind of looked at the table. Now we're going to see how to answer the types of particle motion questions in when they give you an equation. So it says the position x coordinate of a particle moving on the x-axis is modeled by the function x of t is equal to t cubed minus 4t squared plus 3. 4t is greater than or equal to 0, which makes sense. You can never have negative time, so they're going to say that often. Where x is measured in centimeters and t is measured in minutes. So, my phone started moving there. Find the displacement of the particle during the first 2 minutes. So again, we just care when we're talking about displacement. We only care about the start or the end position and the start position, and we're just going to subtract those two. Like over here, you know, we only cared about where it was located at this time and where it was located at that time, take the difference, and then that's our displacement. We don't care about anything that happened in between. So really, after 2 minutes, we're just going to look at what happened at 0 seconds and at 2 seconds. So let's just plug it in. Well, we're going to plug in let's do x of 0. Why did I put a parenthesis there? X of 0 is equal to, if I plug in 0, I get 3. And then if I do x of 2, well, let's see, I get 2 cubed is 8 minus 2 squared, 4 times 4 is 16 plus 3, which is -5. Right? So then our displacement, we're really just going to subtract those two values. We're just going to do x. Why did I put the parentheses there again? X of 2 minus x of 0, and we have -5 minus 3, which is -8 with the units centimeters. Okay, which makes sense. You know, if you started off at 3 meters and then you end up over here at -5, then that displacement is -8. So Now let's talk about the average velocity of the particle during the first 2 minutes. So if we're talking about average velocity, we got to be thinking about the rate, right? So, or just rate of change for the position. So let's figure out, well, we're going to do the position of 2 minus the position of 0 over, 2 minus 0, right? Average rate of change. We already found that earlier. That was -8 divided by 2, -4. So it's -4 for average velocity, and then units, centimeters per, not second, minutes, right? Because this is this is talking about centimeters, and then the units on the bottom are minutes, because 2 minutes minus 0 minutes. So find the velocity of the particle when t equals 4. Well, hopefully you remember from the previous notes that the velocity is the derivative of the position function. So we're going to take the derivative of the position function. So we know x prime of t is equal to 3t squared minus 8t and then plus 0, right? So if you want to know the velocity at t equals 4, that's going to be x prime of 4. When we plug in 4, we get 3 times 4 squared minus 8 times 4. 16 times 3 is 48. 48 minus 32 ends up being 16 centimeters per minute. All right. And then we're going to go ahead and look at this one. Find the acceleration of the particle when t equals 4. Well, we should know that acceleration is the second derivative of this, or the derivative of, or the derivative of our velocity function. So we'll just do x double prime of t, which is equal to, that becomes 6t plus 8. And then if we plug in 4, we get x double prime of 4, which is equal to 24 plus 8, which is, wait, hold on. That doesn't seem, minus 8. Sorry. Minus 8. So 24 minus 8, and that coincidentally ends up being the same thing, 16 centimeters per minute squared. No, this does not always work out like that, but it just happened to work out that way for this problem. And then for this one, is the particle speeding up or slowing down at t equals 4? Well, let's think about it. Remember, if we want to know whether something is speeding up or slowing down, we know that it's speeding up if they have the same sign and slowing down if they have different signs. So if you think about it, well, you have a positive 16 here and a positive 16 there for velocity and acceleration. So we're going to say it's speeding up because let's kind of use a different notation, because the velocity at 4 and the acceleration at 4 have the same sign. Okay. All right. So those are pretty typical types of questions that you would see if you have a position function and they ask for velocity and acceleration. Now let's kind of get into the graph, and this is the one that I feel like is gonna trip you guys up a lot. So if we look at this one, it says that the figure shows the velocity v equals x of t of a particle moving on a coordinate line. So yes, a lot of us are so used to seeing our position graph, right? And then saying, oh, well, the derivative is just the slope of all of this, and then we're looking at the velocity and acceleration. This time, you have to read to see what the graph is about. This is the velocity function. And now you have to kind of go back and forth and start understanding that, looking at the slopes and looking at where it's above or below the x-axis is going to tell you different things than if this were the position function. All right. So hopefully you guys don't get too confused, but let's just kind of look at this. It says, when is the particle moving to the right? And they want you to justify that. So I'm going to start with the justification just to make sure that we understand, and that we, I think if you start with the justification and remember, why, what leads to the answer, that'll help you out. So we know that it moves right, if the velocity is positive. Okay? So where is the velocity positive? Well, we know that it's positive when it's above the x-axis. So we know that from here to here and from here to here, those intervals show when the velocity is above the x-axis. So this occurs at let's just say from 0 to 1, and from I can't really tell. You wouldn't have to guess. I mean, sure, you can use maybe a linear approximation for those of you who know how to do that, but let's just say 4.7 for now. 4.7 to 7. Okay. Now for this one, it's saying when is the particle moving left? Justify. So we know that it moves left if the velocity is negative. Now this occurs at, we're going to say the interval from 1 to 4.7, because that's when it's below the x-axis. So 1 to 4.7. Okay. For number 3, it says, when is the particle's acceleration positive, negative, or 0? So remember, you have to remember that the acceleration is the derivative or the slope of velocity. I've said it before. We're going to use slope, derivative, tangent line, or slope of tangent lines interchangeably, right? So we're going to think about the slope of the velocity or the derivative of the tangent lines. So in this case, they're linear, so you can easily tell what the slopes are. But so if we know that the acceleration is the slope of the velocity, the positive slopes indicate a positive acceleration. So we know that it's positive from, and where's the slope positive here? Well, it's from 2 to 6. That's when it's going upward. We know that it's negative from, oh, I guess here I use an arrow here, I'll just say from. Negative from 0 to 2. And from 6 to 7. Okay? Now, is there ever a point where the slope is 0? Nah. So it's never 0. Okay? Or at least it's never 0 within this graph. Now, when does the particle have the greatest speed? Okay, well, you have to remember that speed does not care whether the sign is negative or positive. It's the absolute value of velocity. Absolute value. So if you kind of look at your graph, you got to say, okay, well, where is the what are the points that have, or what are the points that are furthest away from my my x-axis, my 0 axis, right? So here the velocity is 2. And here the velocity is negative 2, and there doesn't really, if I took the absolute value of any other value, there's not really any that'll be bigger than that. So we know that it's at t equals 0 and t equals 2. That's where it has the greatest speed. All right. And then well, not last, but when is the particle speeding up and justify? All right. So we got to think about, okay, well, speeding up, we got to remember that it's speeding up when both the acceleration, so if the velocity and acceleration have the same sign. Okay, so now we got to, play around with the graph here and say, okay, well, let's focus on two things. Let's focus on when both of them are positive. So both are positive at, so let's think about it. Well, the velocity is positive only in this region and this region. The acceleration, so I'm just going to kind of like, divide it in half. So we're only looking from here and above. That's where the velocity is positive. The acceleration at this portion is negative. That one's positive, but that one's negative. So really, they're only both positive in this region right there. Okay, so above the x-axis and a positive slope. So we know that from 4.7 to 6, that's when they're both positive. You can see. From 4.7 to 6, Okay, and now we're going to focus on when they're both negative. Let me grab a different color here. You'll notice here, so when it's below the x-axis, that's when the velocity is negative. And over here, that positive slope is showing a positive acceleration, so it's not there. But this region is what indicates when both of them are negative. Both the velocity and the slope or acceleration is negative. So we're going to say that they're both negative at 1, 2. So from 1 to 2 in that domain, that's when it's negative. Last but not least, we got to talk about when is the particle slowing down and justify. So we know that it's slowing down, and I'll just write my justification here. When the velocity and acceleration have different signs. Okay? So when they have different signs, we know that it's slowing down. So I wish I didn't write over that, but that's fine. So again, we're going to look over here at the positive portion. Let me just see if I have any other color. I have green. Perfect. So we're going to first look at when let's look for when velocity is positive first. So when v of t is positive and acceleration is negative. All right, so when the velocity is positive and the acceleration is negative. So velocity is positive above the x-axis, and it's negative really in, negative slope, negative acceleration, negative slope, negative acceleration. So we know that that's happening at from 0 to 1 and from 6 to 7. Okay. And then, of course, the other time that we know that the particle is slowing down is the reverse. If the velocity is negative, but the acceleration is positive. Okay. So we know that this is happening down here. So we know that the below the x-axis, that's when the velocity is negative. And then here we have a positive acceleration slope. So we know that that's happening between 2 and 4.7. So between 2 and 4.7. All right. That sums it all up. So sorry for the long video, but this is a very important topic. And I wanted to make sure that I explained everything with as much detail as possible. Hopefully that made a lot of sense to you guys, and the problem set will be posted very soon, and just keep grinding through it. If you're most likely a Calculus BC student, if you're watching this, we're pretty much just doing one lesson a day, and we're just going through and trying to get this. We have to get through all 8 units by December, and that's kind of stressing me out. So I want to make sure that we get there on time, because God forbid you're not ready for the semester exam, and God forbid ultimately you're not ready for the AP exam, because when we get to the actual Calc BC topics, those are going to be very rigorous. So I'm going to let you guys go, and good luck. Have a good one.